Hello everyone. In this video we are going to see another type of PV cells, which is thin film PV cells, or also known as the second generation PV cells. It has a very unique structure and it is also known as amorphous silicon, and why it is that we will be seeing in this video. Solar cells can be made from very thin films of silicon, and such a form is known as amorphous silicon, which you represent as ASI, in which the silicon atoms are much less ordered than in the crystalline forms. We already saw what is a monocrystalline silicon cell and a polycrystalline silicon cell in the previous videos, and here the highlight is that it is made into very thin films of silicon, and such a form is known as the amorphous silicon form. In amorphous silicon, every silicon atom is not fully bonded to its neighbors, which leaves it known as the dangling bonds. And these dangling bonds can absorb any additional electrons that is introduced by doping, which makes the p-n junction ineffective. So to overcome this problem, there is a manufacturing method in which amorphous silicons are made. So it involves a gas containing silicon and hydrogen, SiH4, which is known as silane, and a small quantity of dopant, usually boron, which is decomposed electrically in such a way that it deposits a thin film of amorphous silicon on a suitable substrate, which you can also call as the backing material. So let's see the structure. You can see amorphous silicon, which is acting as the intrinsic and which is placed on the back contract. The hydrogen in the gas, which we mentioned silane is SiH4. So the hydrogen in the gas has the effect of providing additional electrons that combine with the dangling silicon bonds to form an alloy of silicon and hydrogen. The dopant, which we said boron, which is also present in the gas, can have its usual effect of contributing charge carriers to enhance the conductivity of the material. So the dopant, which is boron, which is present in the gas, can have its usual effect of contributing charge carriers to enhance the conductivity of the material. The solar cells, which uses the amorphous silicon, have a different form of junction between the p and n-type material. Usual silicon has a p-n, that is a p-type and n-type, but the amorphous silicon is going to have a p-i-n junction, where you have an extremely thin layer of p-type amorphous silicon on the top, followed by a thicker intrinsic layer which is made of undoped amorphous silicon, and then a very thin layer of n-type amorphous silicon. The intrinsic layer has an undoped amorphous silicon because both the top layer as well as the bottom layer has silane gas present in it along with boron. Now let's see some of the advantages of these amorphous silicon cells. They are much cheaper to produce than those made from the crystalline silicons. It is also a much better absorber of light, so much thinner and therefore cheaper films can be used. And the manufacturing process operates at a much lower temperature than that of crystalline silicon, so less energy is required. But amorphous silicon cells are currently much less efficient than their crystalline counterparts, and the efficiency of many currently available single junction amorphous silicon, it degrades within a few months of exposure to sunlight. These are widely used wherever we have low power requirement. You can see maybe calculators, wherein efficiency is not a bigger problem. So we'll just have a look at comparison of these three types of PV cells. The first one was the conventional monocrystalline cell, which has an efficiency of 18%, followed by the multicrystalline or the polycrystalline cell, which is 17% efficient, and the thin film cells or the amorphous silicon cells or the second generation PV cells has an efficiency of 13%. Thank you.